The band structure is one of the central concepts in solid-state physics. Many fundamental properties of a solid can be understood with the help of the band structure. For example, electrical conductivity, thermal properties, optical properties, and quantities such as effective mass or band gap energy. Indeed, the band structure is the plot of energy as a function of wave vector or k point, as you can see in this figure. To do band structure calculation for graphene, we do 4 steps. The first step is self-consistent field calculation. We did it before. To do band structure calculation, I mean the second step, we do this. We create a folder with the band structure name, and then we copy the content of self-consistent field in it. We copy the content of self-consistent field in band structure folder. Now I open the input file with PWGUI graphical interface. I open the input file and do some changes. I open the input file and do some changes. In the input file, we change the type of calculation and set it into band structure calculation. Also, we change the direction of input, output, and pseudo potential to band structure folder. It should be noted that the name of prefix should be the same as self-consistent field file. We should check it. In the system section, we should check the specification of the lattice. Because we specify the lattice by A, B, C, and etc., we should check it. Sometimes after the opening of input file, it switches on seldom. Thus, I should choose by A, B, C. Then in the system section, in the optional variables, I set NBND, number of electronic states, to 8. Next, we go on the K point tab. I choose this manual crystal specification for band structure plot. In this section, number of K points, we should define the number of K points or number of high symmetry points. I set it to 4 because in this case, I have a 4 symmetric points. Thus, we set the number of K points to 4. After that, we can see that 4 empty rows are created for K point definition. Now I fill it these rows by 0 value. I will change it soon. Then I save the file. From quantum physics, we know that usually Energy is plotted as a function of wave vector in a spatial route and direction, and plotting it in the whole Brillouin zone is unusual and sometimes impractical. We assume that you are familiar with paths in the Brillouin zone. For further details about it, you can use this paper. In this figure, you can see high symmetry points for hexagonal lattice here. Usually a path is chosen to pass from gamma, k, and m points. To define the k path, we open the Xcristin software. We click on Tools and choose k path selection. Now we can select the high symmetry points, for example, gamma, k, m, and gamma. You can see these high symmetry points here, and the number of selected points you can see it is 4. We click on OK. The value of multiplier should be 1. Total number of k points is 4. The number of points in the root is 4 because we specify 4 points. We click on OK, and in the band structure folder, we save it with the name of kpoint.pwscf, and then we save it. You can see the file here. These are our high symmetrical points. I copy these values. We should add these points at the end of input band file. You can see this is the end of my input file. I set the weight to be 20. And then I save the file. This 20 number means that we have a 20 numbers between two high symmetrical points. Thus, between each two high symmetrical points, we created a 20 numbers. I open it with PWGUI interface again. You can see these k point values here. Between each high symmetry point, we add 20 k points between each of them. After that, I save this file in the band structure folder, the name of graphene band.in. Before running, always once we see our input file, then we run the code. Now you can see the run is over. We can see graphene band output file here. In the third step, we should extract band structure data. To do this, we go on PWGUI graphical interface and we select File, New, bands.x input. In the prefix, we enter the same name as a prefix for self-consistent field exactly. Also, we specify the root of band folder and also we specify the name of field band that contains band values. Then I save it. We can see this input file here. Now we should run this input file with bands.x in terminal environment. To do this, I open terminal environment and I write mpi run bands.x, the name of input file, graphene.bands.in. Now you can see that some files are created, especially these files gr.bands.dat.gnu. Simply we can plot it with GNU plot. To do this, I go to GNU plot, then I write plot. Now you can see this is the band structure of graphene. This is the band structure of graphene. Usually the Fermi energy is set to 0 in the band structure plotting. To do this, we define the Fermi energy. We know it from our previous calculation minus 2.276, and then we write plot. We plot it using $2 means column 2. We want to minus all of the second column from Fermi energy, EF, with lines, line width 2. Now you can see the band structure of graphene, and you can see that the Fermi energy is set to 0 value. In the quantum physics, this point is so famous. It is named the K point. The K point is located here where the valence and conduction bonds contact to each other. Therefore, we can understand that the graphene has a no band gap and its band gap value is 0 because the conduction band and the valence band touch each other at this point.